Hello, my name is David Themens, and I'll be talking today about the ionosphere, how it behaves and its dynamics, what that means for communications and navigation systems. So I'll start off by giving you an introduction to the ionosphere, then talk about how the sun and the variability of the sun, namely solar activity, affects the ionosphere and its dynamics. Then we'll talk about how the ionosphere interacts with radio waves and why we care about it, before discussing how we monitor the ionosphere and how we model it. Before I'll finish off with a brief discussion about the direction forward. The ionosphere is a layer of plasma embedded in the upper atmosphere between roughly 80 and 2,000 kilometers altitude. It's predominantly produced by photoionization of the upper atmosphere by energetic photons from the sun. And by virtue of it having high electrical conductivity, it interacts very strongly with the Earth's magnetic field, producing dynamics that are much more complicated than one would expect from a region of our atmosphere. On the right, I just have a little demonstration where when we talk about energetic photons from the sun, I'm not talking about infrared radiation. Infrared radiation is mostly responsible for the heating of the Earth's surface. Visible light, similarly, goes all the way through the atmosphere and is responsible for most plant life on Earth. In the near ultraviolet, that radiation tends to be absorbed by ozone in the upper atmosphere, and hence why we care about the ozone layer. What I'm really talking about is the far ultraviolet and the extreme ultraviolet band of solar radiance. So these bands of solar emissions are sufficiently high in energy that they ionize molecular constituents and atomic constituent molecules in the upper atmosphere. Things like N2, O2, and atomic oxygen. If you go further past the extreme ultraviolet, you arrive at X-rays, where X-rays, in fact, penetrate all the way through the ionosphere to the lowermost regions of the upper stratosphere, and can produce ionization at fairly low heights, causing severe blackout conditions for high-frequency communication systems. So when I talk about the ionosphere being embedded in the upper atmosphere, what I really mean is if we look at the density of different species, either molecules or atoms, in the upper atmosphere, given here in terms of altitude and density along the x-axis, you can see one, the atmosphere decays exponentially as you increase in altitude, and two, if you compare the densities of atmospheric constituents to the densities of ions and electrons in the ionosphere given here, you note that really there are fundamentally fewer ions and electrons, or far less plasma in the upper atmosphere than there is neutral atmosphere, or rather thermosphere. The ionosphere, the lowermost layers, are mostly made up of molecular ions, so NO+, O2+, N2+, produced by photoionization of N2+ and O2+, or N2 and O2 in the lower portion of the ionosphere, below about 150 kilometers or so. Above that, the predominant ion is O+, or atomic oxygen ions, which occupy the peak density of the ionosphere. Above the peak into what we refer to as the topside ionosphere, O+ ions cede their dominance to hydrogen ions and helium ions, which dominate the layer above about 1,000 kilometers, and we typically refer to that as the plasmasphere. So from my description so far, you can tell that it's actually quite challenging to discuss the ionosphere without first having a discussion about the sun. The sun goes through a number of variations, some of which you might be familiar with. For example, it goes through what we call the solar activity cycle, where at low solar activity, the sun looks fairly plain and unstructured, whereas at high solar activity, or what we call solar maximum, you can start to see the appearance of a number of these structures on the sun that we call sunspots. These are regions of where the sun's magnetic field is penetrated up through the thermosphere and are highly magnetically dynamic regions that tend to be the source region for a lot of energetic events that can deeply affect the ionosphere and our upper atmosphere. This cycle generally features the creation of these sunspots around the 30 degrees off the solar axis at the beginning of the cycle, solar equator, sorry, which slowly begin to be produced closer and closer to the equator before eventually decaying and being left with very few sunspots. The maximum in any given cycle is usually in the intermediary between this original creation of sunspots at around the 30-degree latitude of the sun and the eventual decay of the sunspots at the solar equator. The bottom plot here is just a demonstration of the 11-year periodicity of the total area occupied by these sunspots on the solar surface. So you can see every 11 years we go through this fairly consistent cycle of increased variability followed by a lull in activity. So you might ask why we care about sunspots. Well, the sunspot cycle, or the number of sunspots on the solar surface, is directly coupled to the radio emissions from the sun, as well as the extreme ultraviolet and far ultraviolet emission from the sun. And so, since we know that these ultraviolet emissions, or these extreme ultraviolet emissions, are responsible for the ionization of the upper atmosphere, this solar cycle becomes an integral part of the variability of the ionosphere. So, if we look at just the regular variability of the ionosphere, at solar maximum, given by the solid lines here and here, the electron density, or the plasma density of the ionosphere, is substantially enhanced with respect to the density at solar minimum, given by the dashed line here and here. The red curves correspond to nighttime, and the black curves correspond to daytime conditions. You'll note that during the daytime, when we have a substantial amount of photoionization, the ionosphere can be broken up into a series of layers. We have the D region, the lowermost region of the atmosphere. This is generally the region that we attribute to absorption for high-frequency communication systems. Above that, we have the E region, which is mostly made up of molecular ions like N2+, O2+, and NO+. Above that, we have the F1 layer, which is the region where we have the maximum photoionization in the ionosphere. And finally, above that, we have the F2 layer, or the F2 region, which coincides with the maximum electron density, or the maximum plasma density of the ionosphere. Above this peak, the ionospheric electron density decays exponentially into a region we call the top side. You'll note that during the nighttime, even though we don't have a source of photoionization, because the rate at which the electrons and ions recombine in the atmosphere is related to the density of the regular atmosphere, the neutral atmosphere, the lowermost region of the ionosphere decays very rapidly when you no longer have a source of photoionization. However, when you go up to higher altitudes, where the abundance of neutral molecules and atoms is substantially lower, the ionosphere can actually persist throughout the night. And this actually becomes an important or helpful feature of the ionosphere, in that if we want to use the ionosphere for something, it's nice to know that even when we don't have photoionization, when we don't have a source of ionization, it's still there. So that's the kind of quiescent normal variability of the ionosphere. However, the ionosphere also can exhibit a fairly dynamic behavior in the presence of strong, what we refer to as geomagnetic storms, which are caused by storms or eruptions of plasma on the sun. And so here I just have a quick video of what we call a coronal mass ejection from the sun, where you see this loop of plasma surrounding the sunspot region here is ejected from the solar surface out into the interplanetary medium. This will repeat in a second. These are just different coronagraphs or different wavelengths that we're looking at this emission. You can see a little bit more clearly just how massive of an eruption of plasma is coming from this coronal mass ejection. There was also another satellite that was available during this period called Stereo, which was able to look at the CME from a different angle from the side. And it really gives you an impression of just how impressive an ejection of mass this is. To give you an impression of scale, this is the Earth at scale with respect to this loop of plasma that's on the Earth, on the solar surface. So these coronal mass ejections are massive with respect to the Earth and can cause significant disturbances within the ionosphere. So when one of these coronal mass ejections occurs, if it's directed towards the Earth, the embedded magnetic field of this plasma is oriented southward with respect to the Earth's magnetic field. The magnetic field lines of the plasma ejected from the sun can connect with the Earth's magnetic field and drag it into the night side or into the unsunlit side of the Earth, where it'll eventually reconnect in the tail and inject energy into the plasma in the tail, causing a precipitation of particles towards the poles of the Earth, which we refer to as Aurora. This is just going to be a video of some Aurora at Yellowknife to give you an impression of what we're talking about here. So there's a bit of cloud initially, but you can see eventually the Aurora kind of prevails over the cloud. And you can see these really dynamic and kind of fascinating structures that move through the field of view. These auroras are produced by those energetic particles being accelerated in along the magnetic field and colliding with our Earth's upper atmosphere. And the process of that collision, those particles also ionize the upper atmosphere, where the depth at which these particles create ions is dependent on the energy of those, or the speed at which those particles are moving. Very fast, very energetic particles will penetrate deep into the atmosphere and deposit their energy or cause ionization down into the D region ionosphere, which can cause a significant absorption of HF Rios communications, which we'll talk about in a few minutes. You'll note that even very low energy precipitation or particle precipitation can cause ionization in the upper atmosphere at the region, even to the F region of the ionosphere. What this means in terms of that profile of the electron density that you're imagining before, which is roughly given by this blue line here, is that ionization causes a substantial enhancement in the electron density and ion density, or plasma density of the ionosphere given by this black curve here. Similarly, in this situation, where the red curves are actually a model that I made that I'll be discussing later. Unfortunately, the complexity of the ionosphere doesn't end there. The ionosphere is a horribly or maybe fantastically coupled system where we have photoionization from the sun, solar energetic particles, we have interactions with the Earth's magnetic field, we have interactions with the atmosphere below us where large convective systems like thunderstorms can generate waves that propagate up into the ionosphere and cause disturbances and create structures within the ionosphere itself, and can modulate the upper atmosphere. So it's an incredibly complex system, and when you think about it in the context of say how we model weather in our regular atmosphere, you can imagine that the additional complexity leads to some fairly substantial problems in terms of predictability. So if the ionosphere is so complex, why do we care? Why do we bother trying to model it? Why do we spend so much time looking at it? Is it just because it has some shiny aurora that we're drawn to? The reality is that the ionosphere acts as a medium and reflecting surface for high-frequency radio communications. These are communications in the band between 3 and about 30 megahertz, which are a standard in the aviation industry as a backup system. This is particularly important when you have transpolar flights that rely on these systems for communications in the absence of ground infrastructure to tell or to monitor and report the position of an aircraft. If these communications are unavailable, say because of an X-ray flare that enhanced ionization in the D region and caused a complete blackout of HF communications, those flights are required to be rerouted at a significant cost to the airlines. Similarly, by what I mean in terms of a reflecting surface, if the frequency that you're transmitting is sufficiently below what I'll refer to as the plasma frequency of the ionosphere, which is just proportional to its electron density, I won't describe it any further than that, a signal propagated up towards the ionosphere will become reflected. This means that you can have extremely long-range communications by bouncing signals repeatedly off the ionosphere back towards Earth, towards whatever friend you have in Australia or Canada, maybe. This also enables technologies like what we call over-the-horizon radar, which are were popular Cold War radar systems that operate in the HF band and use the ionosphere as a mirror to look around the Earth's horizon. Normal radars can get you or can tell you a target's position out to about maybe 200 kilometers. An over-the-horizon radar system can tell you the position of a target out to several thousand kilometers. In some cases, up to as much as 5,000 kilometers. This is particularly relevant when we start talking about areas that can't have large networks of monitoring radars, such as the high Arctic, where there isn't ground infrastructure to facilitate the development of such a network. So if you have one over-the-horizon radar, you can monitor a significant portion of the Arctic without having to have expensive networks of these radars. Not only does the ionosphere affect the high-frequency band, but also affects signals in what we call the ultra-high frequency, or the UHF band. These are signals in the low gigahertz range, in the low end of the microwave band. And what happens is, as a signal propagates through the ionosphere, it can become distorted. It can be scattered by structures within the ionosphere, and it can be slowed down. The slowing down of the signal becomes a significant problem when you're trying to use navigation systems like GPS that relies on the assumption of the time of flight of your signal being relayed to the distance between the satellite and the receiver by the speed of light. If the signal isn't propagating at the speed of light, you'll cause a significant error in your ability to determine your position. For the same reasons, these irregularities in the ionosphere and this delaying as signals propagate through the ionosphere can cause distortion in radio telescope imaging from the ground. So if we want to effectively use these technologies like GPS or over-the-horizon radar, we need to model the ionosphere. Now, there are two main kind of regimes of ionospheric models, namely empirical models and physical or physics-based models. Physics-based models are incredible scientific tools that require very intricate knowledge of the physics at play in the ionosphere, which unfortunately for the ionosphere is still somewhat under research. Careful information about the drivers of the system, which for the ionosphere is also highly undersampled, and information about the boundary conditions around your model. We need to know what the forcing is, or what waves are coming up from the troposphere, stratosphere, mesosphere, and how those waves are coupling with the ionosphere in our model. And so physics-based models, due to the complexity of the system, have traditionally had trouble being an accurate representation of the ionosphere for operational purposes. And so because of that, very often we've seen the development of these empirical models, which are just fits of various mathematical functions to large databases of data or measurements that we have of the ionosphere. And so what I'm going to focus on from here on out are these empirical models. So empirical models of the ionosphere have been around for quite a while. They tend to come in two flavors. There are global models, the most famous of which is the International Reference Ionosphere, which is recognized by the International Standards Organization as the global standard for ionospheric specification. There's also the International Center for Theoretical Physics, ICTP's NE-QUIC model, which is the kind of go-to favorite model of ESA, and a version of which is the correction model used by Europe's Galileo navigation system. There are also regional models, like the empirical Canadian Hierarchic Ionospheric model, which is the model that I developed as part of my PhD and postdoctoral work, as well as the simplified ionospheric regional model, or SERM, that was developed at the Italian National Geophysical and Volcanology Center. So, unsurprisingly, I'm going to talk a little bit about eShame. So, eShame was built on a large database of ionospheric observations that stretched back all the way to about 1939, where we had the original observations of the ionosphere in Slough in the UK. Ionosomes are high-frequency radars that play on the principle of reflection from the ionosphere to bounce various high-frequency signals in a range of frequencies from, say, 2 to 30 megahertz off of the ionosphere until they no longer get reflected. They then invert these echoes into a profile of the electron density of the ionosphere that's available up to the peak density of the ionosphere. Here we just have an ionosome that's located in Pond Inlet in Canada, where this is the transmit mast, and you can see a few of the receivers on the ground here. So by a lot of these ionosomes, I mean that we've gathered about 80 of them from all around the world, dating again back to those original 1939 observations in Slough. And you can see generally over land we have a very good coverage of observations at least for the electron density of the ionosphere, up to that F2 peak because of these ionosomes. But ionosomes are restricted to propagation below that peak density. And so if you want to look at the density of the ionosphere above that peak, you need to use something like an incoherent scatter radar. These are megawatt VHF radars that transmit high powered signals up towards the ionosphere and measure the scattering of these signals off of the free electrons that in the ionosphere. By doing this, these incoherent scatter radars are able to give you a profile of the electron density or the plasma density of the ionosphere from about 50 kilometers in some cases, all the way up to anywhere between 600 and 3,000 kilometers altitude. So these systems cover a much wider range of altitudes than those ionosomes. The problem, of course, is that these are incredibly expensive systems costing millions and millions of dollars. And as such, there are really only about 8 of them in the world at any given time. In addition to those incoherent scatter radars, you might think, well, why don't we put an ionosonde in space? Well, that was Canada's first satellite. Alouette-1 was simply an ionosonde mounted onto a satellite and using the same principle as the ground-based ionosomes, reconstructing the electron density profile from its orbital altitude down to the F2 peak of the ionosphere. So this is up top here is just an example of some of the echoes that we got off the ionosphere from Alouette-1, October 21st, 1962. In addition to that ionosonde data that I talked about before and the incoherent scatter radar data, we also used this data from these original, what we call topside sounders, to construct an empirical model of the ionosphere. And when you do that, you get nice little representations like this. So the plot on the right is just an example of the log of the peak electron density of the ionosphere plotted spatially at a particular given time. I think it's 10 UTC in February 2012. So in this case, the sun is located over here, and you can see there's a substantially larger electron density in the region where we have photoionization towards the sun, then into the night side, or the region that's not sunlit over here. You'll also note this auroral zone here, where we have an enhancement in electron density surrounding the polar cap. In terms of vertical structure, using fit to those data sets as well as some data on the energetic spectra of Aurora from another satellite called the SUSY instrument on the DMSP constellation, we're able to really do a great reconstruction here given the red dotted line of the vertical electron density profile of the ionosphere at this particular time, where the black line here is given from an incoherent scatter radar. So you might think, well, project's done. Clearly, we have a good representation of the ionosphere. We're happy with it. We can move on. The problem is that empirical models have a number of caveats. For one, they aren't capable of resolving small scales because they're limited by the spacing of the measurements that were available when we fit these models. So what I'm going to show you here is a movie of the integrated electron density of the ionosphere, or the height integrated electron density of the ionosphere, and the electron density at around the F2 peak in this plot here. The azimuthal direction here is magnetic local time. You can analogize to regular local time. And the radial distance here is the magnetic latitude, or geomagnetic latitude. So I'll play that now. So you can see, one, just from the beginning, there are substantial structure here in the ionosphere. And when we have a geomagnetic storm, what I didn't mention to you before is that Also associated with these storms are strong electric fields and currents that modulate the structure of the ionosphere and can cause substantial, strong drift of the plasma. The plasma can move at velocities as fast as 3 or 4 kilometers per second, depending on the intensity of the event. And as such, this can draw plasma into the polar cap and cause mixing and create a bunch of small-scale structures that we can't really capture with these mostly climatological empirical models. So as I mentioned, despite the abundance of ionosomes, there's still a lack of data over oceans at high latitudes, which is a considerable problem, and we're limited in terms of spatial and temporal scales by the original data sets that we had. On top of that, despite having incoherent scatter radars and the topside sounders, the topside sounder missions ended in the late 70s, and incoherent scatter radars are very few across the Earth's surface. So there are very few observations of the topside ionosphere to use in these models. On top of that, these empirical models are incapable of incorporating indirect measurements. And maybe conveniently enough, we have an abundance of indirect measurements. With the prevalence of GNSS, I mentioned before that GPS signals, or as they propagate through the ionosphere, get slowed down by that medium and can cause an error in your position. Well, if you have a GPS receiver that records 2 frequencies instead of the standard 1, you can actually use that receiver to measure the integrated electron density atmosphere along the ray path of the satellite to receiver or path. This means that these abundant networks of GNSS or GPS receivers on the ground, given by the blue dots here and here, are available, viable, and fairly densely distributed measurements for characterizing the state of the ionosphere. Here we have on the left the GNSS receivers on the ground that are available in near real time within about 2 hours. And on the right we have data from, or the GNSS receivers on the ground that are generally available the next day. So there's a considerable number of these receivers on the ground that are incredible measurements that we can't use for empirical models. Similarly, in situ measurements of plasma density from satellite missions are incapable of easily being, used in the original fitting of empirical models. On the right here, I have a very messy demonstration of a day of orbits of various constellations of satellites that have openly available measurements of electron density at the satellite location. You can see these measurements have great coverage across into the oceans and at high latitudes that would really be a considerable aid to our representation of the ionosphere if we could have incorporated them into the these empirical models. Nothing to fear though. Instead of incorporating these measurements directly into the models when we create them, we can, however, assimilate those measurements into those models at a later time. What I'm plotting here, the black solid curve here and here, is the electron density profile that we get from each shame. The blue curve, unfortunately, is the true measured electron density profile of the ionosphere from an incoherent scatter radar. The red, fortunately, is a is the electron density profile that we get from my model after assimilating in GPS and satellite in situ measurements. And you can see that satellite data can considerably change the performance and improve the performance of this empirical model. So to conclude, the ionosphere is a dynamic and complex system that's forced both from above in terms of the sun and energetic particles from the solar wind, and from below in terms of waves from the lower atmosphere. New satellite missions like what will hopefully be coming as the Geospace Dynamics constellation in the US, as well as commercial constellations like Spire of these CubeSat missions, show great promise in allowing us to improve our understanding of the ionosphere and increase our capacity to mitigate the effect of the ionosphere on navigation and communications technologies. Signals and measurements of opportunity through citizen science engagement, like programs that are called the HAMSI or Aurorasaurus, are already showing that by engaging the community of I guess, ionospheric fans, we can substantially improve our understanding of the ionosphere. With that, I'd just like to say thank you. You can download eShame or use its web interface at the link here. If you're interested in that HAMSI thing I just mentioned, or in HF communications in general, you can check out this HAMSI link here. It's a nice community of ham radio operators that are coming together to try and produce an interesting data set that can help us understand the ionosphere. If you're an auroral chaser, you can contribute to scientific understanding and also to fellow aurora chasers' observations by checking out Aurorasaurus at aurorasaurus.com. Or if you want to check out more videos of the Aurora from Yellowknife, you're more than welcome to look at them on the Canadian Space Agency website given by the Aurora Max product here. Finally, feel free to contact me at d.art.timmins@bam.ac.uk for questions about the ionosphere or anything else that you'd like to talk about. Thank you.
Yes, I believe we are live, so we can probably get started. I'd like to start off by welcoming Dr. David Themens from our university's Space Environment and Radio Engineering group with the School of Engineering. Thank you very much for your time and for this wonderful, enlightening talk to kickstart World Space Week. We couldn't have had a better start to the events, especially with this year's theme being Satellites Improve Life. I would also like to thank Space Society for organizing this event and for inviting Dr. David Themens. And with no further ado, we will get started with the Q&A session. And just as a random throw it in there, I guess, can everyone hear me, right? Perfect.
Yes.
Excellent. For all our attendees, we will be monitoring the YouTube live chat. So if you have any questions, feel free to type your questions either in the YouTube live chat, or if you're in the Zoom webinar, please feel free to either use the Q&A function at the bottom of your screen, or if you'd like to ask a question directly, just feel free to. I think there should be an option for requesting to be unmuted, or just unmute yourself and ask a question. Perfect. While we wait for questions on the, oh, we do have a question on the YouTube live chat, my bad. The first question on the YouTube live chat says, do high accuracy GPS providers recalibrate the results due to the location and density of the ionosphere with a high frequency?
Yep. So I guess your standard GNSS receiver that you have in your car or your phone, usually they have an internal model of the ionosphere, a very simplified representation that's used for kind of a first order correction. Usually this model outside of the geomagnetic storms that I was talking about is good enough to get the accuracy of your position down to a meter or less. But when you start talking about applications like mining operators or port authorities that are trying to automate the motion and the operations of their docks or their mine, you need to have precision on the order of centimeter or less. And so when you start talking about that type of precision, you have to start employing much more sophisticated techniques to represent the ionosphere and to correct for that ionospheric delay. So yes, a standard GNSS receiver, if you have a GPS, will use what's called the Klobuchar model. If you use the Galileo constellation, you'll use ESA's AnyQuick model. Those are included in the receiver itself.
Perfect. Thank you very much. I believe that has answered the question quite well, as I see from the comments. While we wait for more questions, I'm probably going to continue asking some of my own questions that I had while going through your talk. With I guess several documentaries that I've watched in the past, we have evidence that the Earth's magnetic field seems to be weakening and is in the process of sort of having its reversal. So I was just wondering, with regards to the ionosphere, how does the flipping of Earth's magnetic field have an impact on the ionosphere specifically and space navigation in general? Is this something that we should be worried about?
That's a really good question, and the answer to it is probably, unfortunately, a bit uninteresting. It's that we have no clue. Our modern understanding of the ionosphere or our understanding of the ionosphere is very modern. We've obviously never experienced a flip in the modern era. Really, there's some basic expectations. So the plasma in the ionosphere tends to move along magnetic field lines. And so if you change the locations of the poles or you undergo a flip, the motion of the plasma or the regular kind of quiescent day-to-day variability of the ionosphere will be significantly changed because of that. On top of that, if the magnetic field weakens substantially, you can get energetic particles that can penetrate through into our upper atmosphere. It can cause some problems for low Earth orbiting satellites. In fact, there's a region in the South Atlantic called the South Atlantic anomaly, where we have an anomalously low magnetic field. And in that region, you can see from, say, the SWARM satellites, or a mission that I've been involved with in Canada called the EPOP, we get a number of what we'll call single event upsets, or periods where we have to reset the satellite in that region where energetic particles or radiation is causing instrument errors. So there's, I wouldn't be too worried about those things. It takes a considerable amount of time for such a thing to happen, and at that point, I imagine we would have considerable modeling capacity to start probing some of those questions a bit better. But at the moment, we're still a bit at a loss.
Perfect. Thank you very much. Because one of the misconceptions I guess I had in the past was that if the Earth's magnetic field starts flipping, I guess, at a faster rate or something, that's something that's worrying. So that does kind of answer a lot of questions. Thank you very much. Since you mentioned the South Atlantic anomaly, it just occurred to me that does this have links with the Van Allen radiation belts? And does this have any links with the ionosphere, and navigation systems would get impacted by that as a consequence?
So for navigation systems, it wouldn't really cause much of an effect. GPS and Galileo and all these constellations are located really outside of the second Van Allen radiation belt in the outer belt. So in terms of the South Atlantic anomaly, there's not really a problem for them. However, if you have low Earth orbiting satellites like SpaceX's Starlink or Spire's constellation, or a number of these low Earth orbiting kind of broadband network satellites that are coming up right now, those satellites could be, I would say there's a non-negligible threat in that region to those satellites. Yeah, I hope that answers your question.
Perfect, thank you. We seem to have another quite exciting question with regards to computer modeling on the YouTube chat. The question goes, how has the reducing cost of high-power computers helped your modeling capabilities? Are you able to model some things now which would have been previously impossible?
Yeah, that's a good question. So The answer is absolutely yes. In fact, even weather modeling of the troposphere, you could almost say that the meteorological community is just waiting for better computing power, because at the moment they can't improve the physics or the the models much. The ionosphere, we've been a bit behind the meteorological community in really employing a lot of advanced computational techniques and into modeling our system, simply because it's a bit harder to handle than the troposphere, your normal weather. Excuse me, pneumonia. But what improved computational capacity really has allowed us to do is start to employ these advanced data assimilation techniques, where we have a huge abundance of ground-based and satellite-based data that's now coming online, and in fact growing exponentially year to year, that we can barely keep up with in terms of being able to incorporate that into our models. And in fact, the biggest barrier to using physics-based models now as operational models for, say, your GNSS receiver in your car, or for mining purposes and things like that, is the fact that computationally it takes too long to run a physics-based model with all of this additional assimilation data to be able to use that in a near real-time sense. So it's helping us considerably, and we hope it continues to grow exponentially with the data, if that answers your question.
Perfect. Thank you very much. I guess my next question is more a question out of just personal curiosity. I'm just curious to know what your opinion would be regarding this particular area. But with regards to cube satellites and satellite constellations such as SpaceX Starlink, which had quite an interesting controversy in the last couple of months, and I believe SpaceX has is planning on sending another launch within a day or two. I believe they sent it today because it's the 5th of October. But just in general, what would your take be on satellite constellations? Although they do seem to have numerous advantages, they do contribute quite significantly to space debris in case of failure, or just in case of observing the night sky. It can be seen as a source of pollution in a way. What would your take on that be?
Yeah, there's an interesting ethical consideration to the management of the space environment, and unfortunately, I think in terms of a policy perspective, we as society have not been very good at catching up to regulating the space environment as well as we really need to. As you mentioned, there's always the question of space debris and the potential for a catastrophic cascade, which could wipe out the environment for use for communications or for any of these satellite mission purposes. I lost track of myself there. Sorry. All this to say is that actually my personal opinion of Starlink is I dislike it. I use I think I mentioned in the talks these incoherent scatter radars, and these incoherent scatter radars are used to scattering signals off of electrons, which are very, 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 very small. And if you put a satellite into the field of view, which is a very large conductor, it's like flashing a spotlight back at your radar. And so it really creates a lot of clutter, and can actually cause disturbances of the receive elements in the radar. It can knock out some of the radar elements. It could be quite expensive if you don't predict them. So personally, not a fan, but as a society, we have to kind of weigh the benefit of having general access broadband globally versus the potential nuisance it is for hobbyists and scientists using telescopes on the ground, as well as again mitigating the effects that can occur due to the increase in space debris or the chances of a catastrophic collision. It's a challenging environment, and we're slowly starting to catch up. I think there's a UN commission, COPUOS, that handles the I guess the safe and equitable use of the space environment that has really started to ramp up operations in the last 5 years or so.
Excellent. Thank you very much for that. And space debris is one of my greatest personal interests in general. And in fact, later in the week, I'm also going to be giving a very short talk on the Kessler syndrome. So I was very, very curious to see what your opinion of Starlink would be in regards to space debris, because I am glad to say I am also not a huge fan of Starlink.
Well, to say one thing, I think you have Sean Elvidge coming in.
Yes, we do.
In a few days. And he's currently the PI of a program for the Swimmer project, which is this UKRI big space environment project. That one of the tasks in that is actually to develop better models of the thermosphere to better predict the orbits of satellites and to predict what the debris environment will look like in the long term. Say the effects of climate change and other things on that. So he might be someone you can maybe probe for those questions as well.
Perfect. Thank you for the heads up. Well, I'm happy to say that we have one more question on the YouTube chat. The question says, when will we be able to create a working real-time modeling system? And how would one change our approach to space exploration and satellite technology?
That's a tough one. Real-time? Real-time's an interesting question because we're almost at the point where we can do just real-time assimilation of measurements into models if we start using more simplistic empirical background models, like I talked about. But the bigger question is not so much whether or not we can do real-time modeling, it's whether or not we can do forecasting. One of the disadvantages to the ionosphere is that it's incredibly highly thermally conductive and electrically conductive. And what this means is when something happens to it, the effect is immediate and tends to propagate throughout the medium extremely quickly. In the troposphere, when you have a disturbance, like say a bomb goes off somewhere or a thunderstorm, generally that propagates slow waves away from that disturbance, and there's a considerable amount of time before that significantly disturbs the state. So predictability of the ionosphere is an incredibly challenging problem that will be the game changer. But it relies on us being able to predict the three-dimensional structure of the solar wind, of those coronal mass ejections coming from the sun, which we have maybe 3 or 4 satellites that can actually observe. So that's a big challenge. We have to predict the magnetic field of of those eruptions from the sun in 3 dimensions, which again, challenging. And then we have to advance our physics to the point that we can fully understand the propagation of how that plasma affects the Earth's magnetic field and how that then propagates into affecting the ionosphere and even the atmosphere. So predictability is really what we're trying to get at. In terms of what that can do to advanced technology, really it just reduces costs for people. In terms of enabling new technologies and things like that, honestly, I don't think our field is really focused on that much. We tend to be a bit older in that we've always been trying to solve these old problems that have been sitting on the bench, and we've never really thought about what we can innovate beyond once we fix those problems. Obviously, the thing I mentioned about over-the-horizon radar, that technology would be significantly assisted by increased predictive capacity. Right now, the biggest barrier to deploying over-the-horizon radars is the model of the ionosphere. If you want to be able to predict the position within a few kilometers, you need an incredibly accurate ionospheric model. So that's that. I hope that answers your question.
Thank you very much. That was quite a thorough explanation. And the person who asked the question says thank you. We have a question from Space Sock on the YouTube chat. They've asked, are there any interesting experiments we can do at an altitude around 1,000 meters related to the ionosphere? We are thinking of a cool payload for our rocket competition.
Yeah, so 1,000 meters is pretty low. You're still well into the troposphere at that point. But if you had, say, a stratospheric balloon or something like that, then you could do things like measure cosmic rays from galactic sources that are impinging on our atmosphere. These tend to get deflected somewhat by the Earth's magnetic field and by the sun's magnetic field. And so you could look at, say, how variations in the sun and the magnetic field could affect the radiation environment in the stratosphere. But at 1,000 meters, you're really, it's, I don't think you could get too much unless you put a giant radio instrument on your rocket, about a 20-meter long wire off the end of it. Sorry.
Perfect. Thank you very much. Seeing that we have nearly approached the end of our time limit, I probably will ask a last sort of, excuse me, sorry, a sort of closing question. What advice or tips or recommendation would you have for any student who is interested in pursuing, let's say, a research career in space environment studies or studies involving space technologies for studying the atmosphere?
Probably a bit general. If you're gonna like apply to grad school, don't necessarily apply based on the reputation of the school. Find a supervisor, find a project that you're interested in, that you can believe in, and you think that you can actually commit yourself to, and a supervisor that's willing to invest in you. Those are the two most important things if you're ever going to consider going into research. It's really having a belief in your project and having a supervisor that's willing to go the extra mile to support you. The institution that you go to won't matter. It will it might have a minor effect on like people outside the field viewing you at an interview stage, but for people that actually understand the field or understand the research, it's inconsequential. They're looking at what you've done, and I guess how good you stand on your feet, not at what institution you attend. So I guess it's a bit not quite a direct answer to your question, but
I think that is actually quite invaluable advice. That's, I guess, one thing that not very many people tell you, that it's more important to sort of have a passion and an interest in the actual project that you want to go for, rather than the name of the institute, which is kind of a huge deal in the students' world.
Yeah, and particularly in engineering, I find it you can kind of get a bit hung up on this concept of the reputation of the institution, but
yeah.
If you're going into research, it's less important.
As a particle physics student myself, I mean, I would also second that. I mean, we oftentimes have heard a lot of conversations about students focusing more on the institute rather than the research itself.
Yeah, I'm a physicist actually, so I'm working in engineering department, but I've been trained as a physicist my entire academic career. So maybe I'm going at this from a similar perspective.
Oh, that's great to know. Well, I think that will probably bring us to a close for this session today. Once again, thank you very much for joining in. This was a very nice discussion that we had with all our viewers and with you, Dr. Themens. And hopefully in the future, if we plan any further events, we will be more than happy to invite you over again.
Yeah, thanks for having me, and feel free to send me any questions you might have at the email I left in the presentation.
Thank you. Just as a shout out for the rest of the events we've planned this week. On Wednesday, Space Talk has provided another talk to us from Dr. Elvidge. And on Thursday, we're going to have a talk at 6 p.m. on the Kessler syndrome. Wednesday's talk is going to be the same time as today, so 3 p.m. Sorry, I missed that out. And then again, on Friday, AstroSoc's secretary is going to give a nice little talk on space weather and how we can use satellites for climate study purposes. If you have any questions about our schedule or about anything in general, about AstroSoc, or if you have any questions for SpaceSoc, please do feel free to leave a message in the chat. I've also entered AstroSoc's email on the YouTube chat, so if you have any questions, please feel free to email them to me. I realized I probably hadn't mentioned this before, but I'm the outreach officer for AstroSoc, so if you have any questions about any events, feel free to find me on Facebook and message me, or send us an email, and we're happy to help. And with that, that brings us to an end to our first event for World Space Week. So happy World Space Week, everyone, and we can't wait to celebrate the rest of the week with you and month. Thank you.